Hello friends, in the last week lecture we mainly focused on longitudinal static stability and how your wing and tail contributed to pitching moment. We saw what were the parameters in order to design your fuselage, what were the parameters in order to design your control surface. Today's lecture will be focusing on the same topic. We will be looking at an example and that will make a better understanding of what we learned in the previous week. But before that, I want to focus on how an airfoil gives us information regarding your design process, or what are the information we get, or how to choose an airfoil. This will be looking at first. So, first topic will be how to select an airfoil, or what are the information we will get from an airfoil. Now, big companies like Boeing or Airbus, they basically go for their own design of airfoil, but for our initial phase we will be looking at a database of huge airfoil which is available and what are the information we get from that. The first graph which we will be looking is CL versus alpha graph. Now, for a symmetrical airfoil, the graph for CL versus alpha is like this, that is, this passes through origin, whereas for a cambered airfoil your CL versus alpha graph will be like this. And what are all the information we get from this graph is your maximum value of CL, this is CL max, your stall angle alpha stall, your angle of attack at 0 lift, and what is the value of CL at 0 angle of attack. These are the information which you get from CL versus alpha graph. Now, the second graph which I will be focusing on is CD versus alpha, drag coefficient versus angle of attack, or in some cases instead of CD versus alpha you will get to see CL versus CD graph, CL CD. Now, this is in the shape of a bucket, and what is the significance of this is, for a particular range of alpha, or in this case in particular range of CL, you can see the value of CD does not change. So, from a design perspective this is beneficial for me, because if I operate in this particular range my drag will not be significant, or drag will remain constant. Now, apart from these two graphs, the third graph which I will be looking is your CM at C/4 versus alpha graph. For an airfoil, you will see a graph CM at quarter chord versus angle of attack, and you will see it will vary a lot. This is for, if in case of a symmetrical airfoil you will see that CM C/4 is very close to 0, but for cambered airfoil this will be much lower than your 0. It will be in negative values, something like this. So, from this I can get the value of CM AC. So, these are the three main graphs which are helpful in order to go forward with my design process, because your wing as well as tail will be using some sort of airfoil, either symmetrical or it will be cambered, and these are the parameters required in order to go for a good design. Now, to summarize what all the information we got from this are: first, camber of an airfoil CL optimum, or we can see this is your CL optimum, this is your CL optimum, because for this particular range your drive won't change or it will remain constant. For camber, with camber of an camber of airfoil, CL optimum and CMAC varies. That is, with increase in camber, increase of camber, your angle of attack at zero lift increases, and CMAC will be more negative. Second point, thickness of an airfoil, your CD minimum changes. That is, CD minimum increases with T by C value. Third point, with Reynolds number, CL max increases and CD min decreases. And fourth point, surface roughness influences your CD min and CL max. These are the points we have to take into account when we look in an airfoil. Now there are different type of airfoils present. There are different series of airfoils, and some of them are your NACA 4-digit series, NACA 5-digit series, NACA 6-digit series. Then there are some Epler series, and each of these airfoils are followed by some numbers. For instance, NACA 6622015, and these number have significance. For instance, this first digit represents series number, that is 6th. Your second digit represents chord wise position, of minimum pressure in 10th of chord. That is, minimum pressure is at 0.6 at x by c equals to 0.6. Now this small 2, this third digit This represents your drag bucket extends plus minus 0.2 around CL optimum, and this last two digit 15, this fourth and fifth and sixth, this represents your thickness. Is 15%. So this is the information which we get from a particular series of airfoil. These are the what this series number tells us is this thing, and what are the plot or what are the information we get from plot we have already seen a few minutes before. After airfoil design, we will be looking at some wing parameters. For instance, how do we choose your aspect ratio? So, effect of aspect ratio. First, effect of aspect ratio on slope of lift curve. We have already seen for a airfoil, we know what is the value of CL alpha, some value say K. In order to transform this CL alpha to 3D, we use formula CL alpha equals to CL alpha, this is for airfoil, divided by 1 plus CL alpha airfoil by pi aspect ratio into E. So, you can see as you change your aspect ratio, the value of lift slope curve will also change. Second, effect of aspect ratio on induced drag. Now, induced drag is given by CDI equals to CL square by pi A 1 plus sigma, where this delta, this depends on your taper ratio, sweep, and other geometrical features of an aircraft. Third is your structural weight. Now we know that wing weight is proportional to A to the or aspect ratio to the power of B, where this B is in the range of 0.5 to 0.79, and we also know that as aspect ratio will increase, your wing span will also increase, since we know that B square upon S is aspect ratio, so B will be root under aspect ratio into area. Now wingspan will increase, so there will be more moment at this root, more wingspan, more will be in the bending moment about this root. As a result, your spars will have to encounter more bending force or more weight. That's why structure weight aspect ratio highly affects your structure weight. And point D is aspect ratio effect on span. As we have already seen that span is actually span is proportional to root under aspect ratio. So higher the aspect ratio, more will be your span, and rather than geometrical or aerodynamic features, this will be the problem of storing. The higher aspect ratio, your wingspan will be too large, and you will have problem of storage and that sort of thing. So these are the effect of aspect ratio on wing design. Now we will be looking at the numerical based on the lecture we did on previous week. We saw what were the information we got from airfoil and what were the effect of aspect ratio on wing design. And now we will be doing a numerical based on the lecture we just saw and what we did in the previous week. So we will be doing this for a small UAV. So these are the information which we have for a UAV, or specification of UAV are weight of UAV is 6 kg, or wingspan is 2.5 meters, tail span is 0.8 meters, cruise speed or velocity is 18 meters per second. Now airfoil details. For wing, airfoil is E197. For tail is NACA 0009. As you know, for tail we use symmetrical airfoil, and it is desirable to use a cambered airfoil for wing. Some other informations which are for UAVs are wing root chord 0.330 meters, tip chord 0.220 meters, and sweep angle 5 degree. For tail, root chord is 0.200, tip chord is 0.150. Now using this information, we have to design what will be the tail setting angle and what will be the tail arm, what will be the position of wing and tail airfoil. First of all, before starting, we have to look at the plot of this airfoil E197 and NACA 009, and we have to derive all the information required in order to proceed for design. So once you look at a data for or plot for E197, you will have following information from that plot. CL max for E197 is 1.2, angle of attack at 0 lift is minus 2.75 degrees. Your slope CL alpha of airfoil E197 is 6.30 per radian. There the you will be getting in degrees, you have to convert it into radian. Okay, similarly for tail, you will be getting CL alpha for NACA 0009 equals to 6.66 per radian. Second information we will get from CD versus alpha graph, that is in what particular range of alpha should I operate in order to have my minimum drag, range of alpha for minimum drag. And third, CM at quarter chord versus alpha in order to get CMAC. And for Kepler 197, CMAC is around minus 0.07. Now second step involves calculation of wing and tail area. Now for the wing, it is mentioned that tip chord is 0.220 meters, your root chord is 0.330 meters. So area will be taking it as an trapezoid, and span is mentioned as 2.5, so this will be 2.5 by 2. Area will be half into sum of parallel sides into distance between them. Since this is a area of half wing, so multiply this by 2, you will get area of whole wing. So this comes around 0.6875 meters square. Similarly, for tail area, CR was 0.2, C tip was 0.150 and span was 0.8 meters. So area of tail will be 0.2 plus 0.150 into 0.8 by 2 equals to 0.14 meter square. Third step is to calculate aspect ratio. We know that aspect ratio is given by B square by S. We already know for wing is 2.5 meter and area we got as 0.6875, which gives me aspect ratio of 9.09. Similarly, aspect ratio for tail is 0.8 whole square by 0.14, which is around 4.57. And in case of tail, aspect ratio is usually between 4 and 5. Step 4 is to calculate CL alpha for wing and tail. The information which we got from airfoil is CL alpha for Kepler 197, slope was CL alpha for NACA 0009 was 6.66. This all are in per radian. Now using the formula for conversion from 2D to 3D, CL alpha is given by CL alpha by 1 plus CL alpha pi aspect ratio into E. Here E we are taking as 0.8, which is equal to 6.30 divided by 1.1 plus 6.30 by pi into 9.09 into 0.8, 4.94 per radian, and CL alpha for tail equals to 6.66 divided by 1 plus 6.66 by pi into 4.57 into 0.8, which will come around 4.21 per radian. Step 5, mean aerodynamic chord and aerodynamic center. Chord and aerodynamic center. Okay. In order to calculate mean aerodynamic chord, there are two ways. You can either use a geometrical method or you can use formula. In geometrical method, you know what are the tip and root chords. This is your root chord, this is your tip chord. Measure this length and extend this, join this length on tip side. Similarly, measure this length and extend this length on root chord CT. Join these 2 points and either join this center to this center, or you can extend this line here also. This will be your CR, this will be your CT, and join these two lines. This will be your mean aerodynamic chord. This is geometrical method, but in case you don't want to work on geometrical method because sometimes the wings are too large, you cannot directly apply this, go for a mathematical formula, which is C main equals to, or mean aerodynamic chord equals to 2 by 3 root chord into 1 plus tau square divided by 1 plus tau, where tau is your taper ratio, that is ratio of tip by ratio of chord. In our case it is 0.220 by 0.330, which will be about 0.67. So your mean dynamic chord will be 2 by 3 into root chord is 0.330 into 1 plus 0.67 plus 0.67 whole square by 1 plus 0.67, which will come about 0.279 meters. Once you have calculated your mean aerodynamic chord, now you have to calculate aerodynamic center. Now since in the question it's already given that you have a sweep of 5 degree, this is suppose some theta, then, and this is your suppose mean aerodynamic chord, then distance from the root x and y from horizontal line are given as x equals to b by 6 into 1 plus 2 tau by 1 plus tau, and y is given as b by 6 1 plus 2 tau by 1 plus tau into tan of theta in degrees. So in our case y will be 2.5 by 6 1 plus 2 into 0.67 by 1 plus 0.67, which will be into tan of 5 degrees, which will be equal to 0.051. As you know, for aerodynamic center we usually take C by 4 as your aerodynamic center. In our case C was 0.279, so AC will be 0.279 by 4 equals to 0.0697. So your aerodynamic center from this horizontal line will be at a distance of y plus c by 4, which is equal to 0.051 plus 0.0697, which is equal to 0.1207 meters. So if this is your horizontal line and this was your root chord, which is 0.330, your aerodynamic center from this point will be somewhere around 0.1207 meters. If you want to calculate x, you can calculate, it will come to 0.58. After all this calculation, you have determined what will be the location of AC from horizontal line or from your starting of your wing position. Now after that, step 6 will be to calculate CL trim or particular value of CL at which you want to operate your aircraft, and what will be the value of Cm naught required. We know that weight of aircraft is 6 kg and velocity is 18 meters per second, cruise velocity. So using formula CL equals to under root of 2W upon rho SV square, we can calculate the value of CL trim, which is 2 into 6 into 9.81 divided by, this is at sea level, we are talking about this aircraft at sea level, into area we got as 0.6875 into V is 18 square, which will come about 0.657. So I want to operate at 0.657. Now if you want to change this value, you have to go for another set of, this is the value I got for CL trim. There can be different cases for which the CL trim can be different. For instance, you can operate at CL equals to minimum drag, that is CL equals to CD naught upon K, where you can calculate CD naught, you can assume at something 0.03 to 0.04, K you can calculate and you will get some CL trim at minimum drag. static margin is given by dCm by dCl, or slope of dCm by dCl equals to minus of static margin. We know that from previous lecture and various lectures before which we have done. So Cm versus Cl graph, if we plot, this is minus static margin, and in order to operate at point 0.657, what will be the value of Cm naught? This is at Cl equals to 0. This I have to calculate what will the value of Cm naught in order to trim my aircraft at 0.657. So let's assume I want a static margin of 15%. You can take any static margin, 10, 15, 20, whatever you like. I have selected 15% as my static margin. So we know that in order for an aircraft to be statically stable, your slope of Cm versus alpha or slope of Cm versus Cl should be negative, as well as Cm naught should be a positive number. But these two has different cases. Here this Cm naught is at alpha equals 0, here this Cm naught is at Cl equals to 0. So I will be doing all my calculations at alpha equals to 0. So in this case, your Cl will the value of Cm naught will be not for Cl equals to 0, but at some value of Cl naught. So this is the value of Cm naught I will be using for further calculations. We have now seen what will be my Cm naught requirement as per Cm versus Cl graph. I have to calculate Cm naught at Cl naught value. So first of all, we have to calculate what will be the value of Cl naught, which is equal to Cl alpha of wing, which I have already calculated, and angle of attack at 0 lift, which we got from Eplar E197 airfoil, which is for E197 Cl alpha wing was 4.94 into alpha at 0 lift was minus 2.75. We have taken modulus, which will be 4.94 into 2.75. This is in degree, we have to convert it into radians, so I will divide it by 57.3, which will give me Cl naught as 0.237. So I have to calculate what will be my required Cm naught at Cl equals to 0.237. We have seen from the graph that my Cl trim position was 0.657 Cl versus Cm. I have to calculate my value at 0.237, and I also know that this is minus 0.15 minus of static margin. So I can easily get this position. Simply I have to do is 0.657 minus 0.237 into 0.15, which will give 0.063. So in order to get a static margin of 15% at Cl trim of 0.657, I have to get overall Cm naught of overall aircraft as 0.063. So now we will see what will be the required condition, what will be the tail setting angle, whether we even require a tail setting angle or not based on these calculations. So this is the Cm naught required. Now step 7. CG your Cm naught of wing, Cm naught of tail. Now earlier we derived what was the position of aerodynamic center with respect to wing horizontal line. This was a horizontal line and we derived as this was 0.1207. As we have already seen in previous lecture, in order to have static stability, your CG should be behind AC. This is your tail. This is your tail. Your AC CG should be behind of AC. Okay. So for a fixed wing UAV, we use a lithium polymer battery. So your mass does not vary with during flight. So we can assume CG is fixed in case of UAVs. But in case of jet, during flight, your consumption of fuel, your CG might change. So you have to consider a range of CG for which you have to do this calculation. But in our UAV, we don't have to worry about that since CG does not vary. So first of all, let me take CG as 0.185 meters from wing horizontal position. .185 meters. You can change this CG and see what will be your result or what will be the tail setting angle. This is just for my calculation. I have selected 0.185 meters. Okay, we derived that this was a requirement in order to have static margin of 15% at CL trim equals to 0.657. So Cm naught for an aircraft or required was 0.063, which is a combination of Cm naught of wing plus Cm naught of fuselage plus Cm naught of tail. For simplicity or in our case, we will neglect this value. So this will be the combination of Cm naught of wing plus Cm naught of tail equals to Cm naught of aircraft. Now Cm naught of wing is equal to Cmac plus Cl naught of wing into x Cg minus x AC by C bar. We have already know what is the value of Cmac from airfoil data, which was minus 0.07. We calculated CL naught wing as 0.237. XCG we have selected as 0.185 and XAC we calculated was 0.127 and C bar was 0.279, which will give Cm naught of wing as minus 0.0154. Once we get the value of Cm naught of wing, we can subtract that from total Cm naught required for the aircraft, which is Cm naught of aircraft equals to Cm naught of wing plus Cm naught of tail. This was 0.063 equals to, we got 0.0154 plus Cm naught of tail. So Cm naught of tail will be 0.063 plus 0.0154, which will be equal to 0.074. So this is a value I have to generate in order to get total Cm naught of aircraft as 0.063. We have already seen the formula for Cm naught of T. Cm naught of T is given as eta VH CL alpha T into epsilon naught plus incidence angle of wing minus incidence angle of tail. For our calculations, we are taking VH equals to 0.7. Typical range is 0.5 to 0.9. We are taking 0.7. So we know VH equals to LT tail arm into ST area of tail by area of wing into C bar. We already know area of tail, we already know area of wing, we know mean aerodynamic chord, so we can get tail arm, which is equal to LT equals to 0.7 into S C bar by ST equals to 0.7 into 0.6875 into 0.279 divided by 0.14, which will give me 0.959 meters. So we got your tail arm as 0.959. So this is your AC, this is your CG, and this is your tail. So distance between CG and aerodynamic center of tail is 0.959 meters. Now to calculate CM, what will be the tail incidence angle in order to get CM naught T equals to 0.0784. So CM naught of tail equals to, let's assume eta as 1 into 0.7. CL alpha of tail we have already calculated. This is CL alpha of tail 4.21, and then epsilon naught plus I of wing minus I of tail. Epsilon naught is given as 2 CL naught of wing by pi aspect ratio, which is equal to 2 into 0.237 by pi into 9.09, which comes around 0.0166. Now substituting all these values in the equation, CM naught of tail equals to 1 into 0.7 into 4.21 into 0.0166 plus IW minus IT. I am not giving any incidence angle to wings, so I will take this value as 0, and CM naught of tail required was 0.0784 equals to 1 into 0.24.2 1 into 0.0166 minus I of t, which will give me I of t equals to 0.01 radian, or something about 0.53 degrees. So this is the value of tail incidence angle we need to have in order to get total CM naught of aircraft equals to 0.063 and static margin of 15% at CL trim equals to 0.657. We have to calculate neutral point. So neutral point is given as X NP bar equals to X AC bar minus Cm alpha of fuselage divided by Cm alpha of wing plus eta VH CL alpha of tail by CL alpha of wing into 1 minus d epsilon by d alpha. Now d epsilon by d alpha is given by 2 CL alpha of wing by pi aspect ratio equals to 2 into 4.94 divided by pi into 9.09, which will be 0.346. And Cm alpha of fuselage, we are taking it as 0 for a time being. So my final equation will be X NP bar equals to X AC bar plus eta we are taking 1, VH we have already taken as 0.7, CL alpha tail we have taken 4.21, CL alpha of wing is 4.94 into 1 minus 0.346, which will be equal to 0.1207. This is the value of AC divided by your C bar, which is 0.279 plus 0.3901 X NP bar. So X NP bar will be 0.4326 plus 0.3901, which will be 0.8227, your X NP bar. If you want to calculate your static margin using formula, static margin equals to X NP minus X CG bar. Once you get this neutral point, you can verify whether my static margin, which I initially approximated, is correct or not. So you can substitute these values in this equation and you will be getting something 0.159, which is 15.9%, which is fair enough since we have taken lots of approximations. So this is determine what will be your tail arm length, what will be your incidence angle, where should be your wing and tail located. I want that you should practice first varying at different CGs and what at different CL trim conditions. Since I took CL trim at 2W upon rho S V square, you can take CL trim at minimum drag, that is I already told CD naught by K, or at minimum power 3 CD naught by K. Try this and you can formulate what will be the conditions or what will be the tail setting angle. So that's all for this numerical. Thank you.